Okay. Awesome. So great. So for our next talk, we have George here to tell us about what statistics we can multi-calibrate. Excited to hear this talk. George is a PhD student and contributing expert on this multi-calibration stuff. Thanks.
Thanks for having me. Yeah. I'm going to tell you guys today about sort of an overall picture of what you can do with multi-calibration when you're interested in eliciting various statistics on your data set. And sort of the goals of today's talk are first to delineate sort of the scope of multi-calibration, what it can and what it can't do, because it's all too easy to assume that, any statistics that we want to elicit, should be possible to elicit, because why not, right? Turns out this is not true. Also, I want to sort of introduce all of us to this connection between, the subject of this workshop and another research area called property elicitation, which I believe has lots of potential in terms of helping us advance our multi-group cause. And third, I want to say that since lots of focus has been placed historically on the binary case, right, where labels are 0 and 1, one thing has been left out of the picture, and this is the fact that if you actually have a more complex label space, then the repository of risk measures that, or statistics or properties, I'm using these terms synonymously today, that you might want to use in various settings, right, to elicit something about the data set that you actually want to know is vast. And some of these, as we'll see today, will have these nice multivalid properties and some won't. So it's very important, I think, that we begin a principled study of various such risk measures. Okay, so yeah, this is what we are doing here, and I want to say that most of the focus has been on multivalid estimation of label means, but recently, and Chris gave an excellent talk yesterday, we've also done something nice with quantiles. In fact, right, the conformal prediction papers have multivalid quantile regression sort of like in the background, right? And today we'll talk about what else we can multi-calibrate essentially. Property elicitation has a growing collection of tools that should help us reason simultaneously about statistics that we're interested in our data, as well as loss functions that we can minimize in order to elicit those statistics as accurately as possible. So think empirical risk minimization, right? And actually, there's lots of nice econ-CS connections to property elicitation. So these property losses, Parikshit should mention in his talk very briefly, actually have these nice truthfulness properties that you can like subcontract a self-interested third party and pay them according to such loss functions, and they'll be incentivized to reveal their knowledge about corresponding statistics truthfully. So lots of nice things. So let's study that. Okay, so this I'm just going to briefly skim over. So we have a data set of feature label pairs coming from some underlying distribution. And the most traditional setting is to assume that the label space Y just consists of 2 elements. And then the Bayes optimal predictor will just give the probability that the coin is up heads for every individual X. And we want to get as close to that predictor as possible while enforcing calibration constraints over an arbitrarily rich family of groups. Okay, so and this is what we mean here, and I'm going to continue using this very informal notation throughout the talk. Yeah, okay, so yeah, as I just mentioned, in the binary prediction setting, the ground truth is basically just a scalar corresponding to each individual in the data, right? Each element of the feature space. And that's pretty much everything that there is to know about anyone's individual distribution, right? So it would be pointless to talk about various risk measures on Bernoulli distributions. Now, as soon as we go to multi-class settings, especially for higher numbers of classes or the regression setting, suddenly many of these statistics start being interesting, and we really want to know what to do with them. Okay. So this is sort of a line of work that we've been doing in our group, and yeah, I hope to sort of like promote it once again here. And today I'll sort of talk about the bird's eye view of this entire line of work, minus the experimentation that was done in some of the prior papers, making it practical. Okay, and let me sort of recap the story so far. So multicalibrated means should satisfy this condition, and as we talked about plenty during this workshop so far, what you do is you keep checking the following condition over various group value pairs. So like on each group and for each value in the range of the current predictor, you check if the expected distance between your predictions and the true label is non-negligible. And if you find something like this, you fix it and you move on until hopefully this converges. And it does, because we can use the squared loss as a nice potential function. Okay. So let's think about this very instructive case of trying to multicalibrate variances, right? So in principle, I could write down the analogous definition just like for means, right? We want to ensure that the conditional variance, given that we're predicting a certain value for the variance, and x belongs to some group, should be equal to that value. So without any further squinting, this looks reasonable. But then if you start trying to come up with an actual algorithm to enforce this, you'll quickly find out that there isn't an obvious candidate to replace this condition that we're checking throughout the mean multicalibration algorithm. And we might wonder, okay, is this some sort of coincidence? Are we just not being creative enough or whatnot? So then we can go back to the fundamentals and we can be like, okay, let's at least check that the ground truth, which we are in the pursuit of approximating, can in fact satisfy these conditions. And for those of you who haven't seen this result, it might sound a little surprising at first, but actually there are very simple counterexamples for when you cannot have this property be satisfied even by the Bayes optimal predictor, right? So let's say our entire universe consists of two individuals, and one of them has label 1 deterministically, and one of them is label 0 deterministically, okay? So point-wise, the Bayes optimal variance predictor says 0. However, now this predictor only has one level set, and that's where it predicts 0, our entire data set. So if we now take any mixture with non-zero weights of both of these individuals, it's clear that the variance will not be 0. And so we cannot actually have multivalidity in the sense that we tried to have it. Okay? So very simple counterexample.
Sure.
Yep.
Can you sort of slow down for a second, just make sure I understand? So you're saying that that sort of at least the syntactic definition, like transporting the syntactic definition of mean multicalibration to an analogous thing for variance does not make sense. In the sense of like the true variance function, like the variance of each individual. Conditioned on the individual, what's their variance? You're saying they're both 0 here, but if you take a mixture over them, the variance is.
Right. Yeah. So the conditional distribution that we're interested in having the variance be equal to our prediction is a mixture over the individuals with whatever probabilities these individuals occur in the data set. So yeah, this like syntactic transformation leads to a nonsensical result, and it's unclear what else we could define for variances. That would be interesting. Yeah.
I don't mean to derail you, but could you just really quickly flash the last definition, the variance one? Do you have?
So the definition is literally that I'm conditioning my labels on the event that I'm predicting a certain value. Yeah, remember that's we have like label.
Where F here is your variance predictor.
Yeah, that's right. So F throughout the talk is whatever we're trying to predict for each X.
Wait, but so if the groups are you and Aaron, isn't the variance?
So the group. So I'm just saying that like Aaron and I are one entire group. So I'm just arguing that even calibration is impossible. So yeah, good point. So what I'm saying today is actually like facts about calibration. to which you can add on whatever groups you want to condition on without any harm to the claims that I'm making.
Sorry, you said something about calibration is impossible. Do you want to say a bit more? What exactly?
Yeah, by calibration, I mean multicalibration where I don't even want to consider any special group structure, just want to consider like this marginal case, right? So here I only have one group, which is everything in the data set. I'm trying to just condition on my predicted values without any further conditioning, right?
So this could also be named multivariance, and multivariance is possible.
So it would be multi if there were like further like partitions into groups, I guess, is what the word multi would mean. So currently just calibrated variance is impossible, but also multivariance is impossible. Okay, so the paper that worked out the mean variance case actually made the following points: that we cannot calibrate variance by itself, but variance, if you happen to know that, let's say, you're currently in the level set of your data set where everyone's label mean is some fixed value, right? So maybe like all the individuals that you're looking at currently have probability of success like 0.6, right? So conditional on that, variance actually distributes linearly across these individuals. So it starts behaving like just like any other linear property, in particular like means. So the approach then is to basically say, okay, it suffices to get a mean multicalibrated prediction for your means, and then since variance is a linear, conditional on that, let's just take the same mean multicalibration algorithm, right? Because variance is a linear, we can like imagine some like pseudo labels, right? That these like variances generate, and then you keep sort of cycling through these two steps until convergence, and it also happens. Okay, so from here we might suspect that linearity is something super important. So linear properties are good to go. Nonlinear properties are in need of some like linearizing property, right? So this is what we might suspect. But actually, this is not quite true because these multivalid conformal prediction papers actually produce multivalid quantiles. And quantiles are, in general, nonlinear. So if you just take any two distributions that don't necessarily have equal 0.9th quantiles, then you cannot just mix them together in any proportionate hope that the mixed distribution will have the same quantile value. So actually, we can calibrate both linear and nonlinear properties, but then some properties are impossible to calibrate by themselves. So what's going on, right? Okay, and how do you calibrate quantiles? And this will give us another lead here. We actually replace the condition that we're checking for means that the expected difference between predictions and true labels is close to 0. We replace it by this coverage condition. So since we're trying to produce, let's say, 0.9th quantiles, then our predictor f of x is supposed to cover the true label with 90% probability, conditional on group value intersections. Okay, so this is a direct analogy, right? And once again, we say that we want this definition of calibration for quantiles, just replace means with quantiles. When you plugged in variance here, it didn't work, but for quantiles, it does work. Okay, so the main part of my talk, and it's really great that I've gotten to it. So, that's, if there's one thing that I want to tell, it's this one. So we will start by proving that the Bayes optimal predictor, so without yet considering algorithmic implications of this, the Bayes optimal predictor for a property is calibrated if and only if the property itself has convex level sets. And what do I mean by this? So a property in today's talk is a functional that takes as inputs a distribution and outputs a single real valued number, okay? And so its level sets will actually consist of families of distributions, right? So a level set for any value that you want to take will be all distributions such that their property gamma is equal to V. And then having convex level sets means that you take any two members of that level set, you combine them with any weights, and it stays within that same level set, okay? So you combine two distributions with the same property value, and it yields the same property value. And in particular, linear properties satisfy this, but this is weaker than the linear condition because here we're only requiring this linear condition to hold when both of the distributions that we're combining have the same value, right? Linearity would mean that they don't necessarily have the same value, okay? So the first direction is very easy. And what we observe is simply that if we try to take our conditional distribution over anywhere that the Bayes optimal predictor predicts V, we're essentially taking a mixture of conditional distributions y given x over some subset of those x for which their individual property value is equal to V, okay? So this is essentially going to be a convex combination, potentially a continuous convex combination. You might need to take the integral, right? So that needs to be handled, but okay. Like, it's going to be a convex combination of distributions in the level set. And since by assumption is convex, that means that gamma conditional in that will also have the same property value, okay? So almost by definition. And the second direction is virtually the same as we saw for the counterexample for variances. So that's essentially the only way that you can fail in general, right? So let's say Aaron's distribution has value V and George's distribution has value V, such that our convex level set's condition is falsified for, you know, the V valued level set, okay? So this is, V is the level set of the property that falsifies the fact that it has convex level sets, okay? And there's going to be some weights lambda and 1 minus lambda such that you combine, you know, some 2 points, right? So let's say it's George and Aaron in that level set, and their combination does not actually give you the same value V, okay? So we write that down and we see that this is exactly the example that we saw before, except it says the same thing now for any property gamma that doesn't have convex level sets, not just variances, okay? So this is an if and only if connection. Yeah, virtually no further conditions that we should require here. But now let's actually turn to property elicitation. And this is sort of like the central notion that, like, you know, I have in the title of my talk, so I better explain what that means. So a property gamma is elicitable if there's a loss function called a proper loss, right? Proper for this specific property, okay? Not proper in general. Such that no matter what underlying label distribution you're faced with, you take the expectation of that loss with respect to like any value that you want to plug in as your guess for what the true property value is. And then the true property value for that distribution will in fact be the minimizer of this loss, okay? So here, if you replace this P with some like empirical samples from P, that's going to be exactly empirical risk minimization, right? You sample a bunch from your data, you minimize some loss, and that's what you get. Okay. Relatedly, a property is identifiable if there's essentially a first order condition that you can solve for, right? So identification function V that also takes in your guess and the label, and its expected value should be 0 exactly when you guessed exactly the right property value, okay? And actually, this does not always have to be the first order condition because maybe your loss is not very well behaved. So like people in the property elicitation community deal with this extensively, okay?
Sorry.
Yep. Mm-hmm.
When we're just thinking about binary labels,
so properties, I mean, you can still have the same setup. So for example, in your talk, right, you gave the example of, you know, the L1 loss, right? That happens to elicit, you know, the binary definition of a median that happens to not be interesting as much as, you know, the actual label mean, right? It says if your probability is greater than 1/2, then, you know, that's what you get. So yeah, for any property that is well defined, is sensible to define on yeah, binary distributions, you can still have the same setup. Yeah. Mm-hmm.
So is that this thresholding, is that it's an elicitable property in your definition? Is the L1 loss considered a proper loss?
Yeah, so yeah, whenever you claim that I can elicit something like the threshold or something for any underlying distribution using this particular loss, that means that it's an elicitable property with respect to that specific proper loss.
This is also the definition of proper loss.
Yeah. So there's also something that's called like just proper loss, not proper with respect to any property, but proper with respect to the entire distribution. And that would be an object that elicits the entire distribution. So the binary case is pretty difficult to wrap your head around because there's some losses that are proper just for means, for higher label space dimensionalities also happen to elicit the entire distribution for binary labels, right? So the boundary is blurred. But yeah, you can essentially consider one of the following tasks. Either you try to elicit the full distribution, which is incredibly hard for non-binary cases, or you try to elicit, let's say, one statistic of your underlying distribution, right? And for each of those cases, if there is a loss that does that consistently for any underlying truth, then that's good, otherwise not. So Megan.
Can you give example of like how to elicit variance?
So you cannot elicit variances, and that follows from the next slide. So this is an incredibly difficult theorem to prove, even though it sounds almost evident from like our discussion so far. The elicitability is equivalent to having convex level sets, is equivalent to identifiability. So in fact, variances do not even have a loss that elicits them. That's why in practice, if you want to know the variance of your data, you first elicit the means using, let's say, the squared loss, right? Or whatever other loss that elicits means. And then you say, okay, let's go ahead and compute the variance given that we think we know the mean from that, right? Two-step procedure there. Okay, so yeah, variances don't have such losses. Quantiles do. For quantiles, this is called the pinball loss, for example. That's a generalization of the L1 loss, right? Slightly weighted. But yeah, so there's this characterization. It's very non-trivial to show, but it basically says that a continuous scalar statistic satisfies all these at once or none of them. And so that means through the convex level sets equivalence, we just showed that a property is possible to calibrate in the sense that the underlying truth is calibrated if and only if the property is elicitable. And I'm leaving out some hairy details that are in the paper, but they should not concern us mostly. Okay, but how do you actually design a multi-calibration algorithm for this? So since I introduced the notion of identifiability and haven't used it so far, that's actually what I'm going to use right now, right? And actually, this first order condition, this identification function, essentially works as a generalized checker. So for any group value pair, you say, okay, let's check what's happening. And if my first order condition is very non-zero, like really non-zero, then I'm going to go ahead and fix that up. Okay. And the convergence analysis of this procedure basically involves saying that the proper loss that elicits this rule will be our potential function. And since we're essentially fixing up its gradients all the time, that means that we're moving towards minimizing that loss. So that's the general picture of what really happens. So yeah, for means, it was the squared loss that was lurking behind this algorithm as the object. That was the potential function. For quantiles, it's going to be some sort of pinball loss, and so on and so forth. Okay, so a negative result, and I'm not going to define this very wide class of risks other than showing a picture that I drew. This is my neat handwriting. So yeah, I'm not gonna say anything else about this class other than perhaps the fact that it operates by saying, okay, like let's say you have a variable. And let's say we want to sort of distort the behavior of this variable in the tails to sort of say, okay, I want to put more emphasis on like bad outcomes that happen, when the variable is very large, right? And so then I can like overemphasize those outcomes, or I can underemphasize, right? A distortion function is any function that starts at 0, 0 and goes to 0, 1 and sort of reweights your distribution. And this is a pretty rich class of measures, includes means and quantiles, includes lots of spectral risk measures, conditional valued risk, and so on and so forth. And so as an illustration of sort of like how we can benefit from property elicitation, property elicitation can benefit from us, we take a result, a very elegant result, has a very nice proof. Actually, other than means and quantiles, like all these distortion risk measures for like any distortion functions that you might want to be interested in do not have convex level sets. So it very neatly tells us, even bypassing the like elicitability is equivalent to convex level sets characterization, very neatly and directly tells us that we cannot multi-calibrate any further distortion risks other than the ones that we already can, means and quantiles. And it's just, you know, a sample result, right? You can come up with more such results. Multi-calibration is not universal. Like that's one evidence. And let me briefly say what happens for the mean variance case, sort of like as a more general picture to actually get insight into this. So I know that some previous papers basically assume that, you know, maybe it's because variances are linear conditional means, so we should always find, you know, some like other statistic that like linearizes you, and that's the only way out. But in reality, sort of from our discussion so far, it's actually evident that the condition is slightly different. It's that a property is conditionally elicitable if there's another property that is itself elicitable. And this new property gamma that may not be elicitable by itself is elicitable on every level set of the underlying elicitable property. Okay, and so this is an example of what could happen. So like, let's say this is the elicitable properties level sets here. They're convex. This is the non-elicitable property. Conditional on each of the level sets of the first property. This is a convex object. Now there's non-convexity as soon as you combine level sets, right? So this like means and this like variances in general, okay? And actually, yeah, the same general family of algorithms will work. You multi-calibrate something that is elicitable. Then you say, okay, let's assume that, you know, I got this, and let me multi-calibrate gamma 1 conditional on our predictor for gamma naught. And then we're like, okay, now gamma naught needs to be recalibrated. And we repeat that until convergence, okay? So yeah, I'm just gonna say that I've been talking about the batch setting right now, but all of this applies to the online adversarial case where you're receiving like sequences of data, and whatever definition of multi-calibration I've been using so far will also be enforceable in the online case with the, you know, batch distribution of data being replaced with the empirical distribution over your sequence of data that you see, okay? And the algorithm will be different, of course, because now you need to sort of like hedge, right, in this online setting. And so it's it can be derived from a certain result, sort of like is a crossbreed of black hole approachability and exponential weights. Okay, and so some summary and perspectives on this. So elicitable properties, right, are equivalent to having convex level sets, and from this we derive the existential truth that, you know, these properties are possible to multi-calibrate, these aren't, you know, the ground truth is or isn't calibrated. Through identifiability, right, which is the first order condition of elicitability, essentially, we derive the actual algorithms for doing so, okay? There's lots of negative results that you could obtain, and I showed you this one, right? You know, there's like so many risks out there, and only so many of them are actually useful for us to look at. And it's sometimes possible to escape non-elicitability when you have elicitability conditional on some other statistics that you are fortunate to have through other losses. Okay, so 2 brief remarks to conclude. First off, sort of like to intuitively relate this to Omniprediction, wonderfully described in Parish's talk. In Omniprediction, you mostly care about loss minimization. So your central object that you desire to study is losses, and then what you do is sort of you harness the power of multicalibration type techniques to sort of like summarize your data in all sorts of multi-valid ways, such that then you can do some data-free post-processing to optimize all the losses that you want and even more, okay? So today we took almost an opposite perspective. We started with the statistics that we wanted to elicit about the data and sort of like try to answer the question, like, do we actually have losses to minimize to obtain those statistics? Because, right, a statistic could be an arbitrary map. Like nobody says that there should be a loss and that it should be elicitable, right? And I'm hoping there will be lots of fruitful overlap between these 2 perspectives. And finally, to sort of relate to a point from Michael's tutorial on Monday, right? So a natural question is, given sort of a class of properties that we want to be outcome indistinguishable with respect to, right? So how do we come up with, you know, distinguishers that will help us efficiently do so? And for at least one-dimensional statistics of your distribution, the answer is pretty simple and comprehensive. If that statistic is elicitable, Then you take the identification function, you take its expectation. If that's too big on some of your data, then you sort of like fire up alarms and you fix that and you keep going. Otherwise, if gamma is not elicitable, then actually there is no sense in talking about OI as it's commonly defined, and you cannot have neither a distinguisher nor outcome elicitability per se. Okay, cool. All right, I'll finish here. Thank you very much.
In the interest of time, let's take any further questions offline and at the coffee break, and we'll meet back here at
3:30. I want to emphasize that the RAM session would not be recorded, won't be on Zoom, so you can feel more free. It's supposed to be fun and
Is this because of your first?
well, see, I need for the first act, we need the volunteers to type. After the break.
Okay.
Okay.